Welcome everyone to our monthly SimCity rounds. I'm so pleased to introduce to you today the first surgeon presenting at our SimCity rounds and also our first SimCity rounds for 2024. And this is Dr. Amin Madani. He's an endocrine and acute care surgeon at the University Health Network, UHN, here in Toronto. He's an assistant professor of surgery and he specializes in the surgical management of thyroid, parathyroid, and adrenal diseases. He's also the director of the Surgical Artificial Intelligence Research Academy, where he leads a multidisciplinary team of clinicians, data scientists, engineers, and game developers. His research focus is in surgical expertise and the optimization of performance in the operating room. This includes using qualitative methodologies to better understand expert mental models, intraoperative decision-making, and other constructs, as well as the development of technologies and innovations to augment and improve surgical performance. These include platforms that incorporate artificial intelligence, computer vision, and advanced simulation. He also serves as the chair of the Global Surgical Artificial Intelligence Collaborative, and it's an academic-led consortium with a mission to democratize surgical care and disseminate surgical expertise to operating rooms around the world. So without further ado, I give you Dr. Madani.
Thanks so much, Dr. Abdul, and for the invitation to present. It's always nice to collaborate with our colleagues around the city. Anyways, I know this is like a little bit different from the psychiatry world or other areas. Definitely let me know if this is of interest to you, if you want to collaborate, and definitely interrupt me at any point if you have any questions. These are my disclosures. I'm not going to talk about any of these. I might talk actually about a little bit about the Global Surgical AI Collaborative, very minimally. But this is okay. So this is what I do. In the city of Toronto, we're very lucky. We live in this like biomedical hub, full of talent and expertise. And we can really cross-pollinate with people in the Department of Computer Science, the Vector Institute. We've got world-class hospitals here and the university. So that's kind of where my lab is, kind of at the intersection of all these places. Like you said, I run a sort of like a multidisciplinary lab. The idea is that, we really focus on the clinical applications, the use cases, and then we collaborate with engineers, computer scientists, data scientists, and so on. And the idea is to bring all that expertise and really innovate at that intersection with technology and education. And the purpose of my lab is really, how do we make surgeons better? How do we make them better, in the operating room, perform at a more elite level? And sometimes that involves, exploring the use cases. Sometimes it involves I like doing a deep dive and understand where the problems are. Sometimes it involves innovating, developing a device, something that involves artificial intelligence. Most of the time, it doesn't involve any artificial intelligence. Sometimes it's something more simple than that. So we work a lot in a multidisciplinary fashion. Our collaborators are kind of all over the world as well. So it's not just multidisciplinary. It's also, we have collaborators from Japan to Korea to Europe to all over the world. We share data together, we train algorithms together, and we collaborate quite closely. And the way I've positioned this lab is sort of, I do endocrine surgery, general surgery, but it sort of provides the sort of infrastructure and methodological support so that other subspecialties can also do this kind of thing. And we kind of provide them with the support that they need to do it. And I've positioned myself such that, if there's like a PI who's really interested in this, I kind of provide like, the support they need without kind of putting this under my own umbrella and my own portfolio. I just kind of help them out, which is a really great way to collaborate with our colleagues. And anyway, this is a little background about me. I thought, for this talk, I'd give a little bit of background. I don't know, people on this call, what background you have in, what kind of technical background you have, but I'll just give some overall high-level description of what AI is, machine learning, deep learning, computer vision, these kind of terms that we use. And then we'll focus on applications of this kind of technologies on how to make surgeons better in the operating room, how we've been applying it for surgical education. And then lastly, what are the challenges for implementing that technology? And there are quite a lot. So what is AI? There's a lot of hype around this technology. Obviously, it's like a buzzword over the last 5, 6 years in medicine. Basically, it's the study of computer science algorithms that give machines the ability to act, to think, and, on a high rational level, like humans, perform cognitive functions, perceptual functions, and so on. And this was really thought to be the stuff of science fiction, but there's been really like an explosion of new advancement, methodologies, and applications. And the lay press is filled with these. It's filled with these examples that you can see. I mean, you can have AI that can write articles for you. This one was done by GPT-3 a long time ago. Now, you must have heard of ChatGPT by now. Large language models that can perform natural language processing, the ability to algorithms to create human language, natural text. In this case, it can write an article. It can, write a poem. This is a poem, about surgical AI in the style of Taylor Swift. So it can really literally do anything for you. It actually sounds kind of good. Students at universities are using it to write essays. Researchers are using it to write manuscripts. Nobody, knows, what to do about that, how to appraise these bodies of work. It's actually interesting. One of the really greatest applications is using this kind of technology for helping write code and programming. So a lot of this has really helped the world of computer science a lot. You must have heard about deep fakes by now. You can literally record a video, apply a filter, and make it look like a celebrity, or the Mona Lisa is actually talking. So it's kind of really scary good. And you can actually now apply someone else's voice on these videos as well. So you can completely make it look like somebody else is actually talking. This one is an example of Leonardo DiCaprio. You can see like David applied filters, to make it sound like it's like other people. I don't know if the audio comes across, but you can see is like talking in like the language of like different people. You got Bill Gates, like literally everybody.
Pretending that climate change wasn't real, somehow make it go away. But I think we all know better than that now.
Computer vision and generative AI has completely changed the creative industry. Graphic designers, music production, animations. You have AI that can create art. What's more human than that? And this isn't just random, random art anymore. You can actually give it a prompt and it'll generate for you what you want. So you can actually write something and it'll create for you something, new and novel. So it's pretty crazy what it can do. And this is and this is obviously spilt into healthcare, this kind of technology. Several years ago, just before COVID started, there was an article in the BBC. I remember reading it where they were talking about how AI outperforms doctors diagnosing breast cancer on mammography, and there's so much of that now in the lay press. So this technology has inevitably spilt into healthcare. Radiology has been really impacted. Pathology is being impacted. Cardiology, neurology. So there's a lot out there, and this is just one example, but there's a million of these. We have journals that are dedicated to digital health now, purely for AI and algorithms and how they're being validated. This is one model developed by right here with us, the clinical camel by Bo Wang, which basically it's like a chat GPT to discuss medical. It's a medical language model essentially. It's pretty good. It's pretty good at what it does. So anyways, that's what AI has been doing. So what is machine learning? Machine learning is a subset of AI. It's really the thing that has been largely, if not exclusively, the thing that has really made AI so popular. Machine learning is about building computer programs that can extrapolate from data. So if you think about traditional computer programs, you have to program everything, like for this situation, this, for this, for that. And then that's how you did it. But for machine learning, it's different. You say, here's, it basically, it allows a program to learn by recognizing patterns of data. You give it large data sets, and then you say, okay, here's so many examples, learn from this pattern. And then when you get new data that it hasn't seen before, it's able to make predictions on that data. That's kind of in essence what machine learning is. Deep learning or deep neural networks is a class of algorithms, within machine learning that has made machine learning very successful. And I'll touch on that in a second. There's different ways you can train an algorithm to make predictions. One of them, the traditional one, is supervised machine learning, which is you give it a large data set and you have to say, okay, for this scenario, this is the outcome. For this scenario, this is the outcome. And you do that for hundreds and thousands of different examples. That's called annotating the data set, giving it meaning, basically. And then you say, okay, here's all these examples, and then you train the algorithm, and then you have a trained model. And then that's it. And it sees new data it hasn't seen before, and it's able to make predictions. So supervised learning is something where you annotate data sets and you give it all these examples. Unsupervised learning is a little different. You don't actually annotate. You say, here's a big, data set, find patterns, that you can find in all this. And it's able to find clusters of data that can kind of, that are similar to each other. This is really important in like e-commerce, for instance, or your Netflix, when it makes suggestions of what you like it looks like at all your search history, it looks like, your profile, your demographic, where you live, all, and it puts that together into, oh, you know what, based on all this, I can say that you fit in this category, and it'll make, recommendations for you. Or like on Amazon, it'll say, oh, this is on sale. Like it knows that you're very prone to buying that. So this is where unsupervised learning comes in. Reinforcement learning is extremely interesting. It's really the closest thing to human learning. Essentially, it's the idea that you say, okay, AI, I'm going to train you to do a task. I'm going to put you in a simulated environment, and your job is to optimize this reward, this function. This is your outcome that you need to optimize. And then the closer it goes to that, it gets rewards, essentially. So it's called reinforcement learning, positive reinforcement, negative reinforcement. And so it plays that simulation again and again until it becomes really good at it. And this is where, it like revolutionary work, and like this is Google DeepMind created Atari Breakout. So after 10 minutes of, I don't know if anybody remembers, this is like from the 80s, I think, but you have like a little paddle and a brick and ball. And so after 10 minutes of training, it's not really good, but after 2 hours of training, it eventually learns how to optimize its score, essentially. And so it becomes really, really good. But what becomes really scary is after 4 hours, not only is it really good, but it actually it figures out these tricks on if you concentrate in a corner, it could get a score even higher. So it becomes really creative at finding solutions, which is really cool. Deep learning, we talked about, this is a class of algorithms. This is like the nervous system. There's input signals, there's multiple intermediate neurons that modulate those signals. And depending on how they modulate, there's different, it can give a different result for different outputs. So for instance, let's say you have a deep neural network that is able to predict, what kind of animal is in that picture. Every single pixel is an input layer, basically, into that neural network. And then the intermediate neurons are things like, the different shapes, different textures, different things. So it's able to, through hundreds of thousands of examples, it's able to say, hey, based on this shape of a beak, the texture of the feather, this color and that color, based on my training data set, this pattern is very highly associated with the bird outcome. So it'll predict that this is a bird. That's kind of in a nutshell how deep learning works. And this has been very successful for computer vision, training algorithms to basically make predictions on images and videos, being able to understand what is happening in those pixelated data. So deep learning has really, really revolutionized that field. So how can you do computer vision? Well, it can look at a frame and be able to say, in this picture, I see a koala. So that's a classification, a frame level classification. It can also localize for you. It can say, not only is there a koala there, but this is where it is with these bounding boxes. You can do object detection tasks. So for instance, like, this is interesting example, you have boxers and it's able to track every time there's a punch or contact that's been made, what kind of hit, where, and it keeps scores that way. This is a student who went viral, who created an algorithm that can translate sign language. So you can do all sorts of really interesting things, basically. Oh, this is me playing with my an algorithm that can track all the joints in my fingers just on my webcam. Like, it's really cool how the technology has come along. So, just think about it. You can train an algorithm that can track your hand motions. You can do so many things from them, like anything from, performance assessment of your technical skills, or, being able to manipulate a structure in 3D. There's so many different applications for this. You can take it one step further and actually make predictions pixel by pixel as well. So not just like, this is the koala, but actually outline the koala or the sheep or whatever it is. So you can get quite specific. But at the end of the day, ML is, it's really for pattern recognition. It's useful for identifying very, very subtle patterns in very large data sets that are, imperceptible to humans. That's really where it becomes powerful, especially when you can combine different forms of data, multimodal data, conglomerate it into an algorithm that can say, oh, this pattern, I can see this. That's where ML becomes really powerful. But at the end of the day, it's a pattern recognition tool. It does not understand the larger context of a problem, just as this cartoon demonstrates. And this is a classic, really funny when this came out. It's you say, draw me a salmon in a river, and it doesn't understand. You're not talking about a fillet of salmon. You're talking about like an actual live fish. So it doesn't understand that problem. There's another example. It's really funny. It's called like draw me an eggplant or something. And then it's like literally these flowers with like the tip is like, instead of a flower, it's like an egg, a sunny side up egg. Like, it's really funny, like how it doesn't understand that problem. So, that's something one has to keep in mind with this technology. Okay, so how do we use this? So it's really cool. How do we use this in the operating room or to improve operative performance? There's many different ways. The field of surgical data science has really advanced over the last 10 years. It was really at its preliminary stages for the longest time, but there's more and more algorithms and proof of concept that have come about over the last several years. It's a very broad field, and I can't, possibly cover everything. That's like saying, how has statistics improved surgery? Like, there's so many different things you can do with this technology. I'll focus kind of on one area. That's my area of interest, which is more the real-time guidance and quality improvement piece. These are kind of interrelated in a way, but I'll touch on all that. So what do I do? So I do work to improve surgeon performance in the operating room. If you kind of think about, what makes surgeons good in the operating room, we always think that surgeons have good hands, very steady hands, but it really has really nothing to do with our dexterity. What makes a really good surgeon, and the data will reflect this, is how well they make decisions, mostly decisions in the operating room. Everything from granular decisions to high level decisions. Those advanced cognitive behaviors are really the things that define surgical expertise. And lapses in judgment or errors in judgment can lead to suboptimal performance that then lead to poor outcomes. And surgical complications are actually one of the highest leading problems, in healthcare. It's definitely an area that's ripe for improvement. Most surgical complications can be traced back to something happening in the operating room that goes wrong, a decision that wasn't made properly. So it's definitely an area that can be addressed. This is my area of research. My type of surgery. I do thyroidectomy. So here I've dissected the thyroid, and this is the recurrent laryngeal nerve. So I'm dissecting on the recurrent laryngeal nerve, the thyroid off of it. So what makes expertise? It's knowing exactly the path of this nerve, the pattern recognition of seeing that this nerve is right there, knowing that there's a plane right above it, knowing that I gotta grab this piece of thyroid and lift it anteriorly to expose this plane. It's knowing that I've got to then rotate with this hand the thyroid the other way. It's knowing that if I get a loss of my signal, that I should just stop the surgery right there and not take out the other half of the thyroid. This collective, this collective bundle of cognitive behaviors is what really contributes to surgical expertise. So now we have a technology that that provides the means for perception and cognition. So can we leverage that? And that's where computer vision has become really interesting lately. This is Tesla's self-driving AI car. It's able to see the world around it. It's able to track, you know, stop signs and the road where you're supposed to drive, where you're not supposed to drive, where the pedestrians are and so on. We want to be able to kind of do that in the operating field, be able to have a decision support systems to guide us, kind of like a GPS for surgeons, to guide and make sure that we don't get into trouble. It's kind of akin to a pilot getting into a cockpit. They don't just fly a plane. They have an entire navigation system to guide them and support them and provide decision support. So that's kind of what we want to try to do in surgery. In surgery, I have to kind of just go for it based on my experience. So we want to improve what we do and augment the surgeon's ability. So this is where we've done a lot of work in computer vision. This is one of the early prototypes of what we've done several years ago. We designed, I said, okay, let's design like a prototype. What's the most common operation we do? It's laparoscopic cholecystectomy. The pattern of error there is dissecting too low along the inferior edge of the gallbladder. So there's go zones and these no-go zones. These are like the safe fly zones, unsafe no-fly zones. If you go below this line of safety, you risk injuring a major bile duct. So you have to keep your dissection up high. And this is a very common cognitive behavior for surgeons. We dissect in very unpredictable areas, uncertain areas. There could be anatomical things that are lurking behind and we can injure. So you have to kind of have an innate sense of which area is kind of safe to start venturing into and which area is not. So we call these go and no-go zones. So we said, can we train an AI to, very binary, go, no go? Can it identify those zones? So we took a data set. We said, okay, let's get an expert panel to annotate these videos of laparoscopic cholecystectomies, annotate the go and the no-go zones. And so we then trained our neural network based on that using traditional supervised machine learning. This was actually during COVID when we went into lockdown, so we didn't have any ORs. So I just sit at home and just annotate video after video. And then we were able to train a neural network that's capable of making those predictions on target structures on its own. And this is what the algorithm looks like. It's able to make independent predictions of where these go and no-go zones are. You can see the green is the go, the red is the no-go zone. And it's able to kind of project what my mental model is on the surgical field. So when I try to take trainees through the case, this is what I try to literally tell them: stay in this safe area. Don't go into this red. That's where injuries happen. So you can see, you can use this for coaching, for guidance, for navigation, and so on. This is a study done by one of my summer students who's there. Sorry, my video is very choppy. Okay. Basically, we took this algorithm and we said, okay, let's see how it does on videos of bile duct injuries. And this is a video where a bile duct injury has happened. You can see that the dissection is, sorry, I don't know why my video is so choppy, but anyways, the dissection is happening very low, like down here. And then the algorithm is saying to keep your dissection high up here. The hotspot red is really where you should be going in this case. And then they end up clipping and dividing this major bile duct down here. So this is how this algorithm can be used. And we found that up to 80% of bile duct injuries can be prevented with this algorithm. That's assuming the surgeon actually listens to the AI. So that's another problem on its own. What have we done since then? We've validated even further. We said, does the algorithm replicate, what an external panel of high volume surgeons would do? And we found that the results are highly comparable. We've done a few other areas. We've removed some of the biases. We've optimized the model. Basically, we've tested different architectures. So the initial model was good, but it wasn't really good for real time and it wasn't really as accurate. These are different architectures. I won't bother through the technical details, but you can see you can use different different AI algorithms to do it. There's different ways to skin a cat. This one is really good for real time. It's very quick. This one is less good for real time, but it's more accurate. Like the overlay is a lot more stable. This is a paper we just got recently published. This is uh, uh, this is one of the collaborative works. So we don't just do in general surgery, also vascular surgery, design an algorithm that can, tell you where not to deploy your stent during a AAA EVAR aneurysm repair. So on fluoroscopic images. This is in colorectal cancer surgery. We're training an algorithm. In this case, this is by one of my colleagues in Japan, who design algorithms that can predict where the oncologic planes are. And this is actually one of the models we are now we're soon going to be doing a clinical trial on to see whether it improves oncologic outcomes. This is another example, a quality safety check during laparoscopic cholecystectomy, something called a critical view of safety, an algorithm that can tell you whether or not you've achieved those three quality metrics before you divide the cystic duct and the cystic artery. This is to prevent bile duct injuries. So algorithms that not only tell you what to do specifically on the field, but also analyze the field on its own to say, you're ready to go to the next step. This is one of the things in surgery that's really important is that we have, one of the things that really makes a surgeon good, and we emphasize so much effort in the operating room teaching our trainees, is how to expose the planes of dissection. You're trying to dissect two things that are close to each other. You have to kind of pull them apart, put them under tension so that you can cut in between. That's like a very general concept in all of surgery. So training an algorithm, in this case, one of my postdocs is working on an algorithm that's able to tell you whether or not your retraction is bad, okay, or optimal. And so that's a frame level classification. And there's new algorithms that are done. This algorithm is able to predict the tissue perfusion before you do an anastomosis in colorectal surgery. So there's a bunch of different examples. These are just a few. It's also been used in surgical education a lot, so especially in performance assessment. So there's algorithms that can track, we talked about tracking your joints and your hands, and if we do technical things, they can also track instruments in the surgical field. So there's at least 24 articles that have come out that correlate the motion tracking of your instrument, everything from, all sorts of kinematics data on the motion smoothness, the completion time, the force, the velocity, the acceleration, the position, the angle, all these things, looking at the pattern of your motion and be able to say who's expert and who's not. So there's quite a lot there. And this is just one example where they were able to correlate that the AI is able to correlate to what expert would rate people on the fluidity of their motions, their economy of their motions, the handling of the tissues, and so on. What was really impressive is that they were able to show that not only is it similar to experts, so it could take away the burden of experts having to to evaluate also, taking away that burden away from them. But more importantly, there's actually less variability between experts and the video based model. So the AI is actually a lot more, reproducible data as well, which is better. It's very rare that we can actually show that, correlate specific things that happen in the operating room to patient outcomes. This one was published just about a year ago now. They analyzed every single move that was happening during a radical prostatectomy, and were able to provide very, very granular data on which one of those dissection techniques was correlated with poor outcomes. In this case, led to erectile function issues after radical prostatectomy. Certain dissection techniques were more associated with one than another. So you can use something like that for coaching. Speaking of coaching, we've been using these AI algorithms for video review and feedback. So we've created this platform where people can upload their videos and, and it'll spit out an analysis of where the, go and no go zones are. So you get some feedback and data. And a lot of our, we've done some surveys and, most people would say that something like that can be an effective adjunct to surgical training. We've also done some gaming. This is really fun. You can actually download this game for free on your iPhone or Android, where basically it's like this interactive e-learning. So you get these scenarios of laparoscopic cholecystectomy, and it says, okay, where do you want to cut, or like where do you want to dissect next? Then you have to like click where you want to dissect, and then it'll basically give you a calculated accuracy score based on the AI prediction. And you can also use it for feedback and so on. So it's really helpful from that. So taking away having a faculty mentor always there to provide you with real-time feedback has been really a game changer. And there's different levels and leaderboards and so on. We deployed this a few months ago. We've had now it's over 1,000 people from over 80 countries who have played this gaming app. It's funny when you turn it into a game, so many people participate. But anyways, we were able to show that there's a lot of engagement and some correlation with level of expertise. So one area that's really hot right now, one of my new master's students is going to be working on is something called synthetic data sets. So I talked to you about deep fakes before. So how are we using that? So there's now algorithms that can take CT scans, segment it automatically, and create these beautiful 3D reconstructions. So they have one group out of Germany has taken that, and they've taken this 3D reconstruction as your input, and then they've created deep fake videos out of this. So someone can take somebody's CT scan, a surgeon can take a CT scan and then put it through this algorithm and then be able to create a deep fake video of what that surgery would look like. So this is actually a deep fake video below. I initially saw it. I was fooled. I thought it was real. But it kind of shows to tell you that, you can actually do things like rehearse an operation ahead of time. So this is kind of very preliminary, but we're getting there. And also there's other areas that you can use AI for, patient flow, resource management, perioperative care. There's algorithms that can tell you exactly what's happening, in the workflow in the operating room. They can tell you what is happening at any point, what kind of things are happening in the surgical field. And just imagine our head nurse at the OR desk is able to track at all times what stage you're at, so we can start planning turnover in that room and things like that. So there's a lot we can do. Perioperative risk prediction is like an area that's really low-hanging fruit in machine learning and improving patient outcomes, and surgical data science. There's a ton of algorithms that can able to predict who's going to die after surgery, who's going to deteriorate, and so on. There's a really cool paper also that was able to take computer vision of the monitor of anesthesiologists and be able to say, okay, based on this art line waveform, this person is gonna, go into cardiac, have some kind of cardiac event within 15 minutes and be able to, make that predictions. So there's quite a lot. Autonomous surgery is also, obviously people think AI, like maybe autonomous surgery. There's just, robots, we have surgical robots, but right now it's very different. Right now it's kind of like a master slave relationship where you're, you have a marionette that you kind of move around in the operating room. The idea is that future robots will have the, autonomous ability to see, to think, and to act. And it doesn't have to be totally autonomous versus no autonomy. Like there's like in betweens as well. You can have something that does automated, suctioning for you, for instance. So there's a lot that this field is just taken off. Okay, I'm gonna just wrap up with challenges. There's a lot of challenges in this field. First of all, model development. We don't actually have good metrics to measure the performance of our models. The traditional computer vision metrics are really good for things like pedestrians and cars and things like that. They're not really good to giving you clinically relevant data. Like they're not good at telling you clinical relevance, how good a model is doing. And that's been one of the biggest problems that we have. And those of us who have done algorithms with things like go and no go and whatever, we're able to see those deficiencies that are not reflected in the metrics that we use. There's also a lack of explainability in a lot of these algorithms. The deep learning is really good at making predictions, but it's not always good at telling you how it came about those decisions. So there is some issues with those. And for all the hype in AI and computer vision, there's actually a lack of evidence and clinical outcomes. Even the area that has done the most, which is colonoscopy and polyp detection, there's been an improvement in things like adenoma detection rate for colonoscopies, but they haven't actually shown that it improves patient outcomes. So maybe those things that the algorithm is detecting are things that are not really clinically relevant. So for all the hype, we don't actually have good patient outcomes on this. And there's actually a consortium, that around the world that's focusing on improving. This is for the metrics to find better metrics. This is a play on word, metrics reloaded, like matrix reloaded. Anyways, that's I didn't come up with that. You need a good roadmap. So if the conclusion is that you're going to develop an AI algorithm that's going to replicate the cognitive behaviors of experts, you have to know the cognitive behaviors of experts. And this is where qualitative research is really important. A lot of algorithms are developed that are completely useless. And that's because no one's actually sat down and done a needs assessment to see what is the problem you're trying to solve instead of, oh, AI is cool, let's use it for this. So this is my background is all in qualitative research, which is understanding where experts make decisions and where errors go wrong. This is for adrenalectomy. I've mapped out all the decisions that happen. So go and no go is like one part out of the entire puzzle, and that's an area where a lot of errors happen. So we need to do the proper needs assessment before we develop these models. Obviously, there's also a lot of issues around ethics beyond the scope of my talk. What happens if there's errors, biases? There's tons of bias with how an AI algorithm is trained. Garbage in, garbage out. So it's only going to make predictions on what it was trained to do. So if your training data sets has biases in it, it'll reflect that. The issues like regulatory approval are becoming, the things that we're noticing. Intellectual property, patient privacy issues. Are patients actually okay with having their data used for training an AI algorithm that's going to be commercialized? Those are issues that we're facing as well. Probably the biggest problem is data acquisition and surgical AI. Videos are extremely rare. It's a lot more rare than getting data from Epic or EMR. Video data is very hard to get, and not only video, like raw videos, but also getting subject matter experts to annotate those data. Like getting like, is it really realistic to expect these expert surgeons from around the world to annotate thousands of go and no go zones, like for every type of operation? Not really. So there are new methodologies that we're exploring to see if we can make the process a lot more efficient. And obviously, there's data from everywhere. We're focusing really on just one area of data, but ultimately the vision in surgical data science is to bring all this data from pre-op, intra-op, post-op, put it all together so you can give really a comprehensive decision support through the entire continuum of care. One of the areas that we've been working on is creating a centralized, space for this data to come together, so that we can use it for research and innovation, so that we can put all our data together and pool it, so that we're not all working in silos. So this is what my work with the Global Surgical AI Collaborative has been, is creating a digital ecosystem for surgical data. Another probably one of our biggest challenges is also implementation. The AI algorithms that I showed you, there's problems with generalizability. So just because you developed a model does not mean if you go to another hospital, it's going to work just as well in that setting. In fact, a lot of times it doesn't. People use different infrastructure, different, videos, different platforms, cameras. So it has to have generalizability. And also these models, you need real-time deployment. How do you do that? Is it really, if you're a lot of the value of this is in democratizing surgical care. If I can train an algorithm to really replicate the mental model of all these experts, how do I get it to people who actually can benefit from this? Is it really realistic to expect everybody to buy heavy hardware in their operating rooms all over the world in rural settings and developing countries so they can bring AI in the OR? Not really. So developing scalable solutions to low resource settings, areas that have poor network connectivity. Like, how are you going to do that? You can get all excited about the hype of AI, but we don't even have a practical way of deploying this. It is one of the areas we've been working on. We've redesigned the architecture of our algorithm so that it's able to work on really any video platform out there. So it doesn't have to be the ones that we use at UHN. It could be really anywhere, and it will help to scale to low resource settings. So we've created what's called an ML data pipeline. So I'm a surgeon in the operating room. I'm doing my surgery, and I can take that video stream using everyday devices like my mobile phone, my laptop, anything. I can actually take the camera on my phone, put it on the monitor, and it'll take that to the cloud. And then the AI will make the inference and then bring that back on my phone for me to see. So if I need decision support, it'll provide me with, that thing. And this is one of the ways we've tried to find a way to scale this. So this is my lab manager who's taking her tablet on the monitor of a video and is able to get real-time inference on where the go and no-go zones are. And this is free for anybody to use. So this is one of the ways we're trying to democratize this. Another way you can do it is with edge computing as opposed to cloud computing. So we've created that cloud solution's good, but it's not great. There's going to be time lag and issues like that. So it's not the most high performing situation. It's a more scalable solution, but it's also not the most high performing. So we've also created this AI in a box situation where it's like a plug and play solution where you have this box and you've uploaded, you can download whatever AI model is available to you onto your box, and you just plug and play into your platform, and it gives you real-time guidance on your monitor. So we've designed these solutions to kind of address that, in your operating room. This is a simulated OR where we have, a video laparoscopic cholecystectomy, and it's on the same monitor that I'm doing surgery. So there's going to be a need for this kind of technology as well. And then finally, we've worked on design issues as well, testing things like usability. How do you want your overlay to be displayed for you as a surgeon? So there's a lot of user interviews and things like that. A lot of human in the loop. One of the things that we worked on is creating a threshold of confidence. So I want the AI to only tell me where the go zone is when it's above 90%, confident of that prediction. There's issues we had to deal with the optimizing latency, the numbers of frames per second. You don't want to send every single frame through your pipeline, otherwise it's going to crash. So we had to kind of do some technical things on the back end. And our data pipeline is actually really good in the sense that it doesn't matter what kind of bandwidth you have, what kind of internet you have. It's able to kind of stabilize across. So that way you can get it to places that have low connectivity and poor network connections. So I'll just conclude by saying, the ultimate vision is, to democratize surgical care. So this is every surgeon's been there. You have a tough case, a tough situation in the middle of the night. You have somebody that you call, to kind of help you and, give you support during the surgery. So my person is my colleague here, Dr. Kai Schwartz. She's an excellent HPB surgeon. She actually does a lot with simulation and education. So I don't know if your circles have run into each other, but just a fantastic surgeon. She's one of my go-to people that I call whenever there's an issue in the OR. Anyways, the idea is now we have a technology that can replicate the mental model of people like Dr. Kai Schwartz, and not just the one here at UHN, but all the Dr. Schwartzes from all over the world. It's able to take all of that and turn it into this like AI algorithm, like a super Dr. Schwartz. And this super Dr. Schwartz is like deployable whenever you want in any geographic scenario. That's the kind of idea of democratizing surgical care. So it's taking the collective wisdom of many expert surgeons and making it disseminated. To me, it's very akin to the Human Genome Project. In a way, it's kind of, you know, bringing all these groups together to develop algorithms that can see the human body from different vantage points for different surgeries, so that we have libraries of AI algorithms that can be used by any surgeon from anywhere. So that's kind of like, you know, that's kind of the vision. So in summary, AI is a very powerful tool for improving surgical care. Computer vision for real-time guidance is really in its infancy. There's so much hype around it. There's actually a lot of other low-hanging fruits that we can do. But really the technology is starting to kick in, and it's up to us to kind of use it properly. There's a lot of obstacles. I wrote UHN here, but anyways, I think we all have a lot to gain from digital transformation to build infrastructure capacity and opportunities both intramurally and globally. Because at the end of the day, this kind of technology can be used to improve quality and safety, resource optimization. You know, like I was telling you guys that one of my master's students is going to use an AI algorithm to optimize how mass casualty trauma patients are transported to different hospitals like that. Like you can do this for so many different things, or provide equitable care. So anyways, that's all I got about AI for surgery. These are acknowledgements. I work with a big team of people, technical people, more clinical people. You know, kudos to my project manager, Kathy, who's my right-hand person, and also Mike Brudno is one of my biggest collaborators. He does a lot of the computer science stuff of what we do. So yeah, thank you.
Thank you so much, Dr. Madani. That was very enlightening. I don't have any really, detailed questions, because obviously my area of expertise is far outside this. But I do remember when I first took on the role of faculty lead, I got introduced to this young entrepreneur who was developing 3D anatomize, looking at making sort of 3D models for difficult surgeries. And I thought about what you said towards the end there, where you were saying that you could use this technology to use deep fakes and recreate unique scenarios. What do you think might be the pros and cons when you think about a 3D model in real life versus, um, you know, cost difference, practical benefits from doing it in real time versus digitally? I wonder about those aspects.
Yeah, I mean, there's a lot. Like you're talking about like creating 3D models in simulation, like inanimate objects, 3D models.
Yes.
Yeah, I mean, there's definitely, I don't think we're there yet in our 3D. I think one of the areas and deficiencies is putting in the physics and the like viscoelastic properties of the tissues into our 3D models. So I don't think we're really there yet. You know,
Mhm.
obviously it'd be great if we had everything in virtual reality that we can just create and have interactive tools that we can get haptic feedback on and so on. But obviously there's a lot of advantages of having a printed 3D model that you can simulate. You know, it's you can get haptic feedback, you can get your instruments in, you can, you know, it's a lot, but obviously the challenge there is cost. You know, building these models can be quite, you know, I don't think our hospital has a lab that does 3D printing for rehearsing an operation. Not only it doesn't have an infrastructure for any of this, so there's definitely pros and cons. But hopefully we'll get to a world where we don't, you know, we can create these things in virtual reality.
Emily Luco was on, but she left. She's the Sick Kids Center manager, and I know they have access to 3D models at Sick Kids. Walter Tavares said amazing work. Thanks for sharing. And he actually
Thank you.
presented, yeah, he actually presented SimCity rounds on the road less traveled, where he talked about the difficulty in getting people to line up for this kind of skill enhancing experience. I know you stressed that, we haven't proved that it could impact patient outcomes yet, and that there's a lot of validity that still needs to be accomplished. But would you say you're exposing this is more to residents as opposed to other surgeons? Like where do you see this so far? The uptake is more likely to be with trainees or across the board?
I think it depends on the algorithm. Like an algorithm like go and no go zones right now, it's really just mostly for trainees. You know, it's hard to get a bunch of surgeons to listen to an AI algorithm. Like there's going to be a lot more skepticism there. Whereas the algorithm to assist in like a mass casualty trauma simulation, like that's more for people that are in practice and are doing things.
Right.
So I think it really ultimately depends on your use case and what you've designed your algorithm to do.
Yeah, that makes sense. Mohammed is saying, incredible talk, Dr. Madani. What deep learning models are precisely being employed for the go, no go zones?
You mean in terms of what architecture? So initially we used PSPNet, then we used UNet, now we use SegFormer. Which one's better? Take your pick. That we don't know. Some are better than others. Like UNet is really good for real-time inference. SegFormer takes a little bit more time, more computational resources required, but from what I see, we haven't validated it yet, but it's a lot more stable and a lot more accurate in terms of its predictions. So yeah, that depends on which, ultimately we're going to have to figure out which architecture is better, and we have better metrics at figuring out which one is better.
Thank you. So Walter mentioned he's juggling some kids in the background there, but he's mentioning that he would love to discuss the assessment opportunities at some point with you.
Awesome.
Yeah.
Well, we should, if there's a way we can systematically, use it for performance, well, performance assessment of surgeons, especially, how do you measure their technical skills? Like we haven't gone there. When you graduate from Royal College, you basically, you write an oral exam and a written exam, and then you have to pass your rotations. People vouch whether or not you have the technical skills to move on to the next level, but video-based assessment is becoming a new area. So if we have better ways of doing things, more reproducibly, more reliably, more accurately, I think it's really the way to go.
Sure. Well, if we don't have any more questions, I'm going to thank you formally for your time and for this wonderful presentation, Dr. Madani. And we look forward to hearing more from you because I know there's probably more exciting research down the pipeline
Thank you so
in
much for
your
having
area.
me. It
My
was a
pleasure.
pleasure.
Okay, bye.
Have a good evening. Bye, everyone.
Thanks. Bye.